Welcome to today's paper reading. Today's paper is titled, Recursive IntroSpEction, Teaching Language Model Agents How to Self-Improve. This paper was published on the AR14 preprint by Yuxiao and colleagues from Carnegie Mellon University. The central objective of this paper is to enable foundation models to exhibit intelligent agentic behavior through introspection, reasoning, and error correction. Even the most advanced proprietary large language models, LLMs, lack the ability to continually improve their responses sequentially. To address this, the authors develop RISE, Recursive IntroSpEction, an approach for fine-tuning LLMs to introduce this capability. RISE prescribes an iterative fine-tuning procedure, treating fine-tuning for a single-turn prompt as solving a multi-turn Markov decision process, MVP. This approach is inspired by principles in online imitation learning and reinforcement learning, proposing strategies for multi-turn data collection and training. Experimental results demonstrate that RISE enables models like Llama 2, Llama 3, and Mistral to improve themselves on math reasoning tasks, outperforming several single-turn strategies. The study also finds that RISE scales well with more capable models, making meaningful improvements to responses without disrupting one-turn abilities. The introduction of this paper presents a novel approach to utilizing large language models, LLMs, as general-purpose decision-making agents. These agents are designed to not only provide plausible text completions but also exhibit interactive, goal-directed behavior to accomplish tasks. This involves mastering two key qualities: seeking information about the task and making decisions that improve over time. The paper discusses the challenge of enabling test-time self-improvement in LLMs, where recent approaches have attempted to repurpose pre-trained knowledge through few-shot prompting. However, these methods often fall short in complex tasks requiring logical reasoning. The authors introduced the RISE algorithm, which stands for Recursive IntroSpEction. This algorithm employs iterative multi-round training and reward-weighted regression to enhance the self-improvement capability of LLMs over multiple attempts at a given prompt. Figure 1 illustrates the Recursive IntroSpEction (RISE) process, which involves iterative multi-round training on policy rollouts and supervision from a reward function. This method trains models to improve themselves over multiple turns. At inference, the final response is determined by running majority voting on candidate outputs from different turns. The method trains a single model to produce and improve answers over multiple turns, which is more than the 2 turns typically studied in related works. This approach necessitates specific design choices, including an iterative on-policy data generation strategy and a training objective that can learn from both successful and unsuccessful attempts. From an algorithmic perspective, this is akin to online imitation learning, where expert supervision is queried on states attained by on-policy rollouts. Additionally, the method converts single-turn problems into multi-turn Markov decision processes, MVPs, collects data by unrolling the current model, and employs offline reward-weighted supervised learning in these multi-turn MVPs to enhance the model's self-improvement capability. Figure 2 illustrates the process of converting single-turn problems into multi-turn Markov decision processes, MVPs, and the data collection methods used in the RISE approach. On the left, the problem formulation shows how the state in the MVP is defined by the prompt, the history of prior attempts, and optional feedback from the environment. The action is a response generated by the language model, LLM, based on the current state of the multi-turn interaction. On the right, the data collection process is depicted, where the current model is unrolled -1 times, followed by an improved version of the response. This improvement can be achieved through self-distillation, where multiple responses are sampled from the current model and the best one is used, or through distillation, where oracle responses are obtained by querying a more capable model. The generated data is then used to train the RISE model. Figure 3 illustrates the 2 inference modes for the RISE model. The first mode, with oracle, allows the model to check its response against an environment and terminate early if a correct answer is found. The second mode, without oracle, involves the model sequentially revising its responses multiple times, with the final response determined by majority voting on all candidate outputs from different turns. This approach helps avoid test time distribution shift by maintaining a history of the most recent interactions. Figure 4 illustrates the probability of the true answer given a prompt, highlighting that the model trained with RISE exhibits a higher probability for the true answer compared to classic fine-tuning methods. This observation underscores the effectiveness of RISE in enhancing the accuracy of model responses. The figure also compares the training negative log likelihood, NLL, loss, showing that RISE reduces this loss more significantly, indicating better model performance and lower perplexity. Figure 5 illustrates the training perplexity, or loss, when fitting either only the oracle answer or a sequence of answers. The data clearly shows that the RISE method, which fits a sequence of answers, results in a greater reduction in loss compared to the classic method, which fits only the oracle answer. This suggests that RISE's approach to modeling the target distribution through the computation of tokens from previous turns is more effective in reducing perplexity during training. Figure 6 illustrates the effectiveness of RISE in solving problems that were previously unsolved by pass at B at the first turn. The x-axis represents where is calculated as 5 times. The graph shows that RISE, through its sequential 5-turn sampling approach, can address several challenging problems that even larger sampling budgets at the first turn cannot. This highlights the unique capability of RISE to tackle complex problems through iterative refinement, demonstrating its superiority over traditional sampling methods. Table 1 presents a comprehensive comparison of RISE with other approaches such as self-refine and GLOR, along with various baselines. The key observation is that RISE achieves the largest performance improvements from 1 turn to 5 turn without an oracle, and this gap widens when oracle early termination is allowed. Self-refine's performance degrades when used without an oracle but shows minor improvements with oracle feedback. GLOR, which trains a separate refinement model, still performs worse than RISE. The table also highlights that using RISE on a better base model like Mistral 7b is effective, with its 5-turn performance exceeding state-of-the-art math models. Running single-turn SFT on data utilized by RISE is not effective in inducing self-improvement capabilities, emphasizing the importance of RISE's algorithmic design choices. Table 2 illustrates the performance of RISE with self-distillation on the GSM-8K dataset. The table shows that RISE is capable of enhancing the 5-turn majority at 1 performance of the model, even when the base model, Mistral 7b, struggles with producing correct answers for several problems. This improvement is achieved through the use of entirely self-generated data and supervision, demonstrating RISE's effectiveness in sequential performance enhancement. Table 3 evaluates the out-of-distribution generalization capabilities of RISE. It shows that models fine-tuned on datasets like math and GSM-8K can still improve their performance on entirely new datasets such as FAMP. This indicates that RISE's self-improvement strategies are not limited to the distribution of the fine-tuning data, but can generalize to new, unseen prompts. The table highlights the positive performance improvements achieved by RISE on these out-of-distribution prompts, demonstrating its robustness and effectiveness in enhancing model performance across different datasets. The experiments conducted by the authors focus on understanding the impact of various factors on the performance of RISE. Firstly, in terms of data composition, they found that training with multi-turn interaction history, which includes error correction, leads to better performance compared to one-turn data. This highlights the importance of context in training. Secondly, regarding weighted learning, using reward-weighted reinforcement learning on multi-turn data showed improvements over imitation learning with filtered data, emphasizing the benefit of leveraging all available data. Lastly, the source of data also plays a crucial role. An on-policy rollout approach, akin to Dagger, demonstrated superior performance compared to using expert data alone, addressing distribution mismatches in context tokens. Figure 7 illustrates the critical factors in training RISE. On the left, it shows that using multi-turn interaction history and weighted objectives significantly enhances self-improvement performance over one-turn data with oracle answers. The right side demonstrates that incorporating all rollouts, including unsuccessful ones, yields better learning outcomes compared to filtering for only successful rollouts. These findings underscore the importance of context and data diversity in improving model performance. Figure 8 illustrates the impact of different data sources on the performance of RISE in the GSM-8K dataset. On the left, it shows how using an Oracle model, expert, sampling from the learner, on policy, and selecting the best sample out of 16, best of n, affect performance. On the right, it compares RISE's performance with Oracle error feedback to parallel sampling of 5 responses at turn 1. The results indicate that sequential sampling with RISE consistently outperforms parallel sampling, especially as the number of iterations increases. Figure 9 illustrates the changes in the correctness of responses over multiple turns in RISE, without the use of an oracle. The data shows a consistent increase in the fraction of responses that transition from correct to correct, indicating that the model is improving its ability to maintain correct answers. Simultaneously, there is a decrease in the fraction of responses that remain incorrect, suggesting that fewer problems are being answered incorrectly over time. Additionally, the fraction of responses that transition from correct to incorrect also decreases, further supporting the iterative improvement capabilities of RISE without external verification. In the related work section, several key methodologies are highlighted. Firstly, the concept of chain of thought prompting is explored, where an empirical study identifies critical factors that enhance reasoning capabilities in large language models. This approach includes techniques like self-consistency to improve the logical flow of reasoning. Secondly, the development of embodied agents is discussed, focusing on the integration of large language models into open-ended, interactive systems. This includes the concept of self-rewarding models that can reinforce their own learning processes. Lastly, various self-improvement techniques are examined, such as recursive introspection, which teaches models to learn from their own mistakes, and hybrid instruction tuning, which combines different methods to enhance model performance. These methodologies collectively aim to push the boundaries of what language models can achieve in terms of reasoning, interaction, and self-enhancement. Table 4 compares the performance of models on the GSM-8K dataset using different methods of incorporating correct-to-correct data in the RISE framework. The results show that appending a successful rollout with a novel correct response significantly boosts performance, achieving the highest gains. The default RISE design also shows strong performance, while repeating the same correct response at the end of a successful rollout reduces performance, likely due to inducing spurious correlations from data duplication. Table 5 presents the weak to strong generalization performance on GSM-8K, comparing RISE when trained on rollouts from Llama 2-7b versus Mistral 7b. The data shows that training Mistral 7b on Llama 2-7b generated rollouts significantly improves performance, especially in multi-turn reasoning. Conversely, training Llama 2-7b on Mistral 7b rollouts results in worse performance, indicating that the quality and nature of errors in training data are crucial for self-improvement capability. Figure 10 illustrates the percentage of correct responses that change to incorrect responses across consecutive turns for different model configurations. A continuously decreasing trend suggests better self-improvement performance. The boost configuration shows the poorest performance, with the highest overall percentages and an increase from turn 4 to 5. Repeating a correct response shows the lowest initial percentage but increases from turn 3 onward. Both default RISE and appending a different correct response demonstrate a favorable trend, steadily decreasing from 12.3% to 3.9% and from 9.8% to 3.3%, respectively. Table 6 presents a comparison of RISE with other approaches including self-refine, GLOR, and VSTAR, as well as various baseline approaches. The data reveals that RISE achieves the most significant performance improvements between 1-turn and 5-turn evaluations on both GSM-8K and math datasets without the use of an oracle. This performance gap widens further when oracle early termination is permitted. In contrast, the self-refine approach generally results in performance degradation across all models when no oracle feedback is available. GLOR, which trains a separate refinement model, still underperforms compared to RISE. In this study, RISE demonstrated the most significant performance improvements when transitioning from 1-turn to 5-turn evaluations, without the aid of an oracle on both GSM-8K and math datasets. The performance gap widens further when Oracle early termination is permitted. In contrast, Self-Refine showed a substantial degradation in performance across all metrics, despite modifications to the evaluation pipeline to align with the Self-Refine approach. Glore, which trains a distinct refinement model, also fell short in comparison to Rise, highlighting the superior efficacy of Rise in self-improvement tasks. These findings are further illustrated in the key comparison provided in Figure 11. Thank you for watching.